What would you do if a disaster powerful enough to shake an entire nation struck one of the world's largest hydroelectric power stations? Most projects would be abandoned. Most governments would step back. But not this one. After a catastrophic turbine accident that shocked the engineering world, Russia launched an enormous recovery effort unlike anything seen before. Engineers poured a staggering 24 million tons of concrete, rebuilt critical systems, and transformed this giant structure into one of the most powerful dams on the planet. In today's episode of Datascope, we're diving deep into the incredible story of Russia's mega dam, the devastating accident that nearly destroyed it, and the engineering comeback that stunned the world. From massive turbines and gigantic spillways to one of the largest concrete structures ever built, this is the story of determination, innovation, and engineering on an epic scale. Let's begin. Harnessing the power of the river allowed the Soviet Union to access cheap electricity, leading to the creation of the Sanashinaskia power plant, which became the energy heart of Siberia. After decades of operation, a tragic incident occurred in 2009 when Unit 2 was destroyed due to broken bolts, resulting in the loss of 75 lives and marking one of the worst hydroelectric accidents of the century. Despite the disaster, the dam body remained intact, averting a potentially more catastrophic situation. The project officially began in 1963, but before construction could proceed, Soviet engineers faced the daunting challenge of diverting the Yenisei River from the site. This ambitious task was crucial for the successful completion of the dam and highlights the complexities involved in such large-scale engineering projects. The Yenisei is one of the largest rivers in the world, with a substantial volume of water flowing through its canyon daily. I found that the construction site was in Siberia, where winter temperatures often drop below -30 degrees Celsius, complicating operations with frozen ground and reduced construction time. To address this issue, engineers opted for a river diversion method, creating a system of tunnels through the mountains. Construction teams drilled and blasted rock to establish diversion tunnels capable of handling the river's full flow during dam construction. Once the tunnels were completed, upstream and downstream cofferdams were built, requiring the transport of millions of cubic meters of earth and rock to narrow the main flow and redirect the river into the diversion system. Pumped the riverbed inside the cofferdam area dry and removed layers of silt and sediment that had accumulated over thousands of years after completely diverting the Yenisei River. Following the diversion, I initiated a large-scale foundation treatment campaign, using drilling and blasting to remove weathered rock and unstable soil above the bedrock. I excavated over 10 million cubic meters of material, revealing stronger rock masses underneath, and conducted a detailed survey of the bedrock surface after completing the excavation. I identified, cleaned, and treated natural cracks in the rock using high-pressure grouting, drilling thousands of boreholes to pump cement grout deep into the foundation. While reinforcing the foundation, I also constructed inspection galleries and technical tunnels inside the bedrock. Utilized structures that allowed engineers to access the foundation area for monitoring purposes during the operation, focusing on water seepage, deformation, and stress. Construction of the dam body at Sanashinaskia began only after completing all foundation treatment work. I divided the dam body into multiple blocks, pouring concrete layer by layer and stage by stage rather than constructing it all at once. The severe climate conditions of Siberia posed significant challenges, with short summers and extreme cold in winter causing sharp temperature fluctuations. I had to tightly control the hydration process of the cement to prevent dangerous cracks from developing due to temperature differences between the core and the surface. To solve the problem, I continuously monitored the concrete temperature with a system of sensors while carefully calculating the concrete pouring schedule to limit thermal stress. A large-scale material transportation network operated almost nonstop to supply concrete to the construction site, allowing the concrete to gradually stack up layer by layer. As the Sanashinaskia Dam rose higher in the western Sayan Canyon, It faced the critical challenge of managing the reservoir behind it, which has a capacity of over 31 billion cubic meters of water. During flood season, the reservoir can pose a serious threat due to the immense weight of water, necessitating adequate flood discharge capacity to prevent pressure beyond design limits. Soviet engineers undertook significant drilling and blasting operations to establish a construction platform for one of the crucial spillway systems of the project. After pouring concrete to form water channels and energy dissipation basins, I saw the installation of large steel gates and mechanical control systems to manage the flow of water. Engineers diligently tested the flood discharge capacity of the entire system using hydraulic models and flow calculations. Recognizing the dam's role as an energy storage place, I understood that building the Astonishing hydroelectric power plant was essential to convert water into electricity for Siberia's industrial zones. Excavations were made below the dam to create space for the turbine hall and generator hall, reinforcing the foundation to support the significant structures. As the power plant's construction progressed, I witnessed the pouring of concrete for its framework, designed to withstand immense water pressure and the weight of electromechanical equipment. These structures functioned like arteries, channeling water from the reservoir to the turbines, converting potential energy into kinetic energy. After the water flowed through the pressure pipes and spun the turbines, it was discharged back into the Yenisei River. Despite the completion of the dam and hydroelectric power plant, electricity generation was not possible until the largest hydroelectric units were installed. These massive machines, which could not be transported as a whole, had to be manufactured in parts and assembled on site. Heavy-duty cranes were essential for positioning the components, with each generator's rotor weighing around 920 tons, forming a complex electromechanical system intended for long-term operation. The greatest challenge I faced was not the installation of the machines in the power plant, but the precision required during their assembly. Each generating unit would operate at around 143 revolutions per minute, and even a minor misalignment could lead to significant issues. Months of alignment, concentricity, and vibration checks were necessary before the equipment could function. Ultimately, Astonishing was outfitted with 10 generating units capable of producing up to 6,400 megawatts, making it a remarkable energy project. Unfortunately, on August 17, 2009, a disaster struck when the anchor bolts of Unit 2 failed after years of abnormal vibrations. In just a few seconds, the enormous water pressure blew apart the upper structure, displacing a 920-ton generator rotor and causing water to flood into the machine hall. The disaster resulted in the deaths of 75 people, marking it as one of the most serious accidents in hydropower history, although the dam itself was not at fault. Despite the devastation of the power plant, the Astonishing Dam remained intact and continued to hold back the reservoir safely. Following the accident, Russia initiated one of its largest hydroelectric power plant restoration programs, removing thousands of tons of damaged equipment and replacing old generating units with new technology. Stricter safety standards were implemented by redesigning control and monitoring systems and installing a series of sensors to detect early signs of abnormality in the generating units. Carried out the restoration process in stages to ensure the electricity supply for the Siberian power grid, while gradually bringing the plant back to full operation, culminating in 2014 when the final generating unit was connected to the grid. Behind the 242-meter high concrete wall lies the Astonishing Reservoir, which formed a massive body of water over 300 kilometers long with a capacity of about 31 billion cubic meters, significantly altering the terrain of the area. The reservoir stretches out like a vast inland sea and acts as a huge storehouse of energy for the Astonishing system, enabling stable electricity production despite seasonal changes in the Yenisei River's flow. Beyond electricity generation, the reservoir plays a crucial role in flood management by retaining water from melting snow in spring and releasing it downstream in a controlled manner. During periods of low river flow, The stored water in the reservoir continues to support power generation and stabilizes the flow of the Yenisei River. Today, Sino-Shinskaya serves as a crucial provider of electricity for Siberia, underpinning Russia's position in the global aluminum industry. Aluminum production demands significant electricity, with costs heavily influenced by energy prices, making stable and affordable hydropower essential for competitiveness. The hydropower system on the Yenisei River, centered around Sino-Shinskaya, has been vital for the operation of Siberia's largest aluminum smelting complexes for decades. As Russia aims to enhance energy security and decrease reliance on fossil fuels, Sino-Shinskaya remains a strategic national asset. More than 50 years after its construction, this project has evolved beyond a mere dam or power plant to become a key component of the modern Russian economy. And that concludes the incredible story of Russia's mega dam engineering marvel built with an astonishing 24 million tons of concrete and strengthened after one of the most devastating turbine accidents in hydroelectric history. This project stands as a powerful reminder that even the greatest setbacks can be overcome through innovation, determination, and engineering excellence. If you enjoyed this journey into one of the world's most remarkable megaprojects, don't forget to like, share, and subscribe to Datascope. Turn on notifications so you never miss our next deep dive into the world's biggest construction projects, engineering wonders, and technological achievements. Thanks for watching, and we'll see you in the next video.